Start streaming, start recording, and I think we're live. Hello, everybody, and welcome to T3 Alliance. This is a special episode of our weekly show. I've got my intro video here for us to get ourselves started, and we'll see in the background T3 Alliance as we get going. Dun da da da. Welcome to T3 Alliance. So as always, this is one of our 20 lessons. Today we're going to talk about, and before we do this, I have to introduce the people I have here with me today. This is Jefferson Chang. He works with Geological Survey, and he's also a passionate Raspberry Shake person. And then over here in the corner, that's Gabriel, as my son. And we have a few other people in here. There's Ben. You'll meet him a little bit later. And Chester's in the back working in the shop and that kind of stuff. But what we're working on today, first and foremost, we're going to take a quick review on what basic seismology is and basic physics, and then we'll learn about what a professional seismologist does. Fortunately, we have Jefferson here to help us with that. We'll learn about this little tiny seismometer called the Raspberry Shake, and then we're going to set it up in the simple mode, and we're going to set it up with the advanced mode, the mode that is related to this thing that you see behind me up here. Yes, this is actually measuring micrometers per second? Yeah. Something like that. This is a little shake that's over here. Watch this. If I hit this table, then we should see these numbers go crazy. That's pretty cool. It's like a live in your classroom seismometer, and there could be a big rumbling truck going by. There could be an exciting something happening, and or an applause meter or something, and we could learn about it. So with that being said, let's take a look at what we got today. First, seismology. Jefferson, how's that definition? The study of seismic waves. Is that a little simplistic?
It's very basic, yes, but it covers it.
Covers it. So in one corner there's a picture of what what basic geophysics is all about, where people go out and search for what's under the ground by having a bunch of very careful little geophones set up, and then they have seismic events that can kind of trigger some sort of a reflection off of a surface there, and you can learn about what layers of underneath the earth look like.
Yeah, it's kind of like when you're receiving a present, you don't know what it is. You shake it and you find out, hey, this might be this, just by the shaking or the sound of it. So that's what they're kind of doing.
And in this one, this is like one of the simplest seismometers. It's just a mass on a string with a piece of paper.
Right.
And you pull the piece of paper in a forward motion at a constant rate of sorts. And if the earth is shaking in that direction, then you happen to get a measurement of it.
Yeah. So the idea is that since the ball is suspended, it shouldn't move when the earth shakes. And so if it's not moving and the paper underneath it is moving, it's going to get scratched and leave a mark of how much the earth underneath it has moved.
Yeah. Cool. So, of course, this is all about studying how earthquakes work. This is one of the big jobs that seismologists have. And when we think about earthquakes, there's all the exciting pictures that come from, oh my gosh, a big earthquake. I'm not sure where this one is from, but look at the destruction of that roadway that happens. But when we work backwards from earthquakes, we know it's all stress in one of three big categories: tensional, compressional, and shear stress. Tensional is pulling apart, compressional is squeezing together, and shear is like side to side, trying to rip a piece of paper from one side to another. I put a picture in here of a stick that's under tension until finally it breaks. How does that metaphor work for a seismologist?
For seismology, the earth is always moving because of tectonic plates moving, and because of asperities or ridges, the roughness of these faults, they're stuck. And once enough sort of motion far away from these faults take place, the idea is that these roughnesses or asperities will break on their own. Sort of like if you're trying to sand sandpaper, you're not always going to be stuck, but it's kind of rough moving. You're going to have some stuck parts and then smooth, stuck, smooth, or stick, slip, stick, slip. And after that, once that slips, that's when you generate your earthquakes.
Cool. And that is the part that is the exciting part, the moment of excitement for that few minutes there. If we boil it back to the motions that are caused by, if we looked at earthquakes, Yeah, it's about the study of wave motion. Um, when one of those breaks, asperities is the word you use there. When one of those breaks happens, that energy gets released in a way that kind of fits with a drop of water or a rock hitting a pond, and it radiates out in all the directions at about the same rate that energy does, but there are parts of that wave or parts of that energy that move in a faster and a slower rate.
Right. So if you think about it, if you throw a rock in the water, it'll create waves. If you throw a rock in a pot of honey, it'll also create waves, but it won't either go up as high or it won't transmit as much. So that's the amount of energy that's transmitted through that depends on the medium, not the rock.
Oh, I see.
So it depends on what kind of rock you're living at, on whether you're going to feel magnitude 3 or not, kind of thing. Depends how the Earth is going to react.
Got it.
To that energy.
So there's 3 typical waves. The one is called a P wave, a pressure wave.
Pressure wave or primary wave.
Primary wave, yeah, and that would be demonstrate. A slinky would have been a great example to put in here, but
slinky or an accordion.
Yeah, when you hit it on one side, the wave travels across that surface. And an S wave, it's a side-to-side motion.
Yeah, if the P wave or primary wave or pressure wave, the wave propagation travels along with the direction of travel, which is the red arrow. So the wave moves like this, or the particle motion like this. The S wave, secondary wave, or shear wave, the wave still propagates this way, but the particle motion is perpendicular.
Got it. And then what is a surface wave?
Surface waves are a class of waves that come after S waves. They are basically permutations, or just, how do I explain this better? They're a way of particle motion that travels after the shear wave, and they're the most destructive usually because they move a lot, and they move a lot differently. For example, like I said, P wave moves like this. S waves are perpendicular. This particular surface wave is what we call fancily a retrograde elliptical, or a loop-de-loop. If you imagine a roller coaster, what you're doing is this retrograde elliptical if you're flipping around, and that's sort of what your house is going through once this type of wave is going by.
I have a video clip I found here that shows what it looked like in a Costa Rican shopping mall during, I don't know when this earthquake was, but 2005. There we go. So watch this lady right here. She just felt the first P wave, and or the first wave. There it goes.
So this is the P wave shaking side to side, and then you have the S wave, and then this would be the surface waves hitting.
Wow. Wow.
And when it's just shaking every which way.
And is there a relationship between your proximity to wherever the shaking began and how long a distance it is between? Why, yes.
Yes.
Yes. So here, I'll go on to our next picture, and we'll take a look at what a graph looks like. Here's a seismograph that I found on somewhere, Iris. And notice the mass that wiggles when the Earth moves. So boom, you get your first P wave motion, and then we get our S wave motion right after that, and then we get even more ground motion that occurs after that, which goes along with it. And notice if this time scale here, that's a measurement of just how long it's taken for that wave to reach the point. So if we're thinking on a pond where we threw that rock in the water, however far out your boat is how long it takes for those little waves to get to you as you're moving through there.
Yeah.
Now this gets used by seismologists like Jefferson all the time. When an earthquake occurs, if they have access to multiple seismograph stations where they can measure stuff, if they can compare the length of time between when the P wave arrives and then the S wave arrives, they can think about it like the rabbit and the tortoise problem, that classic one.
Yeah, basically when the race starts, when the rabbit and the tortoise, rabbit and the hare, I'm saying the same thing. The tortoise and the hare start the race. That's when the earthquake starts. You see that on the 0 part on the lower left diagram? Can they see the mouse?
Yep.
Oh,
yep,
yeah.
They can.
So they start somewhere down here, and once it goes and travels, once the earthquake travels a certain distance, you can see here in 2,000, 4,000 kilometers, they start to separate. So
that's...
Yeah, so right about, say, 2,000, the separation between the P and S waves are about approximately 4 to 5 seconds. Once they travel up to 4,000 miles or kilometers away, they're at about 7 to 8 kilometers. And the farther you go, this distance increases. So that we can kind of predict, okay, this station, we can see the P, we can see the S, and then we know the time that they came in on. We'll fit it on this graph and say, okay, this station must have been 2,000 kilometers away. We don't know what direction, so we draw a circle around it. And if we have enough of these stations, these circles sort of meet at a common spot, and that's how we determine the epicenter or where this earthquake might have taken place.
Yeah, on this picture, which is one of those classic ones from geology instruction textbooks, there's three seismograph stations here, and each of them has a distance between when the P and S wave. All they know is that distance equals
the radius of where this earthquake likely happened.
Yeah, and then when they line up, the more stations that they get, you can imagine the closer and closer you can get to where they all overlap each other just perfectly. And so our world, of course, when seismologists figured out that they could do this, they put seismograph stations in all over the world. And this is a map over here on this side of where all the IRIS stations are, all these red dots, and then the USGS stations, and then affiliate stations around the world that get used whenever a big earthquake occurs to map out where that epicenter came from.
Yeah.
So that's a big part of your job, right, Jefferson?
Yeah.
What about other things than just earthquakes? Can we detect that kind of stuff?
We use them to locate basically anything that shakes the ground. Here in Hawaii, we use it to monitor the volcano, and not just because of the earth slipping, but whenever magma or underground lava moves through the cracks, it sort of shakes those rocks, and that creates earthquakes or tremors. And that's how we can find out the more tremors we have, it means that more magma is moving underground. We better be careful or be more alert. There's also machinery that shakes things underground, nuclear blasts. If a country out there were to set one off illegally because of the nuclear ban treaty, everybody would know because it shakes the whole earth. That's how powerful these nuclear weapons are. There's mine collapse. There's atmospheric explosions like meteors exploding. They're basically thunderstorms we can monitor, but it's whatever puts
shakes
waves.
Wow.
Through the ground or in the air sometimes.
Wow. Well, that's pretty exciting. If we put up a whole bunch of sensors at one time and we could monitor them in real time, this diagram that I found from IRIS shows what a magnitude 7.9 earthquake would look like across the United States during a real eruption. So this is what kind of in the last 20 years, or how long has it been that we've been able to have real-time, like...
We've been able to have real-time for a while now, but digital sensors actually came on board around, I don't know, maybe early 2000, late 90s.
So what are we seeing here? Can you?
Here we are seeing each circle is a seismic station or a seismogram, a graph. And then the red is an up motion, the blue is a down motion. So whenever these stations measure up and down motion of the ground that they're sitting on. And what you're seeing is the ground motion, how the United States or North America is moving in response to this earthquake in Nepal, so far away across the world.
And if we zoomed in on just our little teeny tiny area, we could see that much detail if we had a great enough density. You can obviously tell Northeast North America has got a lot of seismograph stations, and way out here in Nevada, there's only a few.
A handful, yeah.
Yeah.
So usually states with more seismic activity or earthquake activity will have more seismic networks or seismic stations put out.
Wow. Cool. Okay, so now we get into the world of a typical seismograph. What are these seismographs? Boy, what's involved here? It looks like there's a GPS antenna so that you can get real-time data sent out.
Yeah, basically a system, a top-of-the-line station would cost anywhere from $80,000 to $100,000. You have to dig a hole. This hole particularly is about usually it's about 6 feet deep, but this one says 9.5 maximum. You put concrete underneath, then you have your expensive sensor down there, expensive digitizer. All that wire has to come out. That has to be sealed so no water or animals go in there. Then you need power, solar, a lot of batteries, GPS for the time, and then basically the workers to put them in and maintain them.
Wow. And this is the old school, what they used to graph drums with.
Yeah, these are helicorders, or helicorder plots that are a needle scratching the paper, sort of the classic what we were just showing in those cartoons earlier.
Right. Cool. Okay, well, here's what the Raspberry Shake, this is what part of our talk is about today, is this little device has really revolutionized things because it's brought a $100,000 piece of equipment down to a level of something that you could put in your classroom. They're, whatever, $300 or $250 or whatever it is. But what's its components? It's got like a magnet and this little thing over here is called a geophone. Is that right?
It's a geophone. Basically, it's what it's shown there in the diagram. There's a little mass inside that's surrounded by a coil spring, and once the mass moves, we know from physics that when you have a metal in coil, it produces voltage or current, and those currents get put out in the electrodes, and that voltage gets translated into the Raspberry Shake, which is this blue chip right next to the geophone there. And that gets processed by the software and gets sent out to the cloud for processing. Cool.
Here's a model with an actual Shake attached to it, and with a Raspberry Pi attached to it at the bottom. So we use Raspberry Pis in here a lot. This one over here is a different model they have. What is this thing? Does anybody know?
It's a boom.
Oh, that's
a boom.
So it's an
infrasound. It's a pressure sensor.
Oh, okay.
So like I said, things that create waves in any medium, geophones are usually for the ground, and infrasound is for the air, so the air pressure.
Got it.
Like you can measure thunder and
an explosions like done on the ground would create both seismic waves and an air pressure wave.
Right.
Or an avalanche might create both seismic and air pressure waves or something like that.
Yes.
Cool. Okay, so this is off the website for those guys. These are the types of things that can be detected with a small little citizen science device like this. On a natural level, earthquakes, tremors, landslides, underground water movement, volcanic eruptions, sinkholes. Those are in certain geological environments. There are vacuums underneath in the cave-like structures.
Right.
Sometimes those guys collapse, right?
Right.
And then fracking. Whoa, what is fracking?
Fracking is when the energy industry drills a well, and that well is the rock around it is so tight that they have to create fractures, a fracture network, sort of like. No, I have no example for that.
Okay.
But they just create a bunch of cracks so that they can sip the oil out of the ground more easily.
And then it looks like rush hour traffic, construction, footsteps. Well, obviously with the example that we've got behind us, if it's sensitive enough to notice my hand shaking this table gently, then probably it's sensitive enough to pick footsteps up or somebody coming into a room. Anything that you can feel must be able to be motion like that. So that's pretty cool. The other part of the Raspberry Shake network is that it's the Raspberry Shake is that you are automatically part of a network that isn't the ISIS or the what do you call it? The IRIS, not ISIS.
Not ISIS.
In the USGS network, this is a network around the world of Raspberry Shakes that have been put in, and there's certainly big blank spots where there aren't very many Raspberry Shakes. But here we have one in Hawaii, and if I click on this link and zoom in a little bit, I can see that here's a spot here in Volcano, and over the course of this last period of time, these last 10 minutes, I've had this much sort of shaking that's gone on, and I've got the micrometers per second, the velocity, the displacement, and I can download the information from this worldwide network of shakes that are located around here. So that's cool on its own. All you got to do is just plug this thing in and do the basic setup, and we're going to do that in just a little bit, and you'll be able to be connected to this international network of other people who are looking at each other's data that's collected from here. Is that that pretty much?
That's pretty much it. Everything is open source. You can develop your own software if you want, but there's a lot of software out there on the internet that will let you sort of play around, be a hobbyist, locate your own earthquakes in your local community, or do whatever else you want.
Cool. So let's go ahead and do this. Let's set it up so that we can get it to this level. The first step we like to always remind everybody is, as you know, in this tutorial and this video here, I'll put links to all this stuff down below so you can check it out. But in the event that you've just got your Raspberry Shake from us and you're ready to do stuff with it, if you don't have the latest image, you can follow this link and figure out how to get the image so that it sets up on your own computer. It's basically, you're going to program this little SD card so that when you plug it in and you hook it up to a network, you're ready to roll. And then this is an important slide that I just want to point out. Your Shake is the thing in this image right here, and it's going to be plugged in hopefully to your classroom, hopefully to some place where it can just remain. If you're lucky and you've got an air quality meter or you've got some sort of a display thing, then you can have the Shake plugged in and you can log into it and you can see stuff on it. But where you put it, it stays there, and then it needs to connect outside of your school or whatever environment so that it can go to the Raspberry Shake servers out there. And that's how it needs to figure out what time of the year it is and all that kind of stuff, and then it can share it with everybody in the world. There's a whole nother aspect of this thing where we connect this thing right here to other Shakes, or no, to other Raspberry Pis that your student has in the classroom. And that's when we can do the next level of cool stuff with this, which is hooking it up so that if I, shake the table, not only will, it recognize the shaking and tell it around the world, but it will make an alarm go off on my Raspberry Pi. And that's kind of like cool, because it means that you can make an alarm, or you can make some sort of a meter that does something when a shaking of this magnitude happens. And that's a local connection that we'll be setting up. So that's what we're going to go to next. But I think right now we're going to go to, hey, let's set up your Raspberry Shake the first time. And I pulled this video off the website, but let's just go live here because we have a Shake set up in our own area, and we can talk about what we've got here. So with that being said, I'm going to tilt the camera over here. Gabriel and Jefferson, you can see where we are. Here comes Ben. Ben's one of the other guys in our room, and he's going to talk us through. Here's the Shake that you get. So Gabriel, can you make sure to zoom in and out? I don't know if you guys can see over here so that we can see what you guys got going.
Yep. So this right here is the actual Shake and the Geophone. This is the digitizer that goes on top.
Your hand that way. There
this
you go.
Is the digitizer that goes on top of the Shake. And you should get in your kit these 3 pieces along with this platform. So to start connecting it, we set up, you could first put the digitizer on top of the Shake by connecting it to the GPIO pins. And it doesn't connect to all the GPIO pins, just the ones on the farthest side from the USB ports and such. So that should be how it looks. You can set this up here. We're not going to set it totally up now, but once you have it plugged in, then you should be ready to plug in power, and then here is our connection. This is our Ethernet cable. So I think plug in power first, and it should show up. The blue light here means that the Shake it's on. It sees itself. It knows what's going on, and this just means your Pi is working. Then we can come and connect the Ethernet in, and hopefully I don't see a Ethernet light in there, but we'll see if the oh, yep, I do see a light. So if you can see a light inside the Ethernet cable, it usually means it's on. Sometimes it doesn't. But now its green light is on. It's connected. So it's now doing its thing. It's trying to broadcast out to the world. And now that it's set up, we can go find it on our computer and remote in. What the Raspberry Shake is what a lot of people like to call a headless Pi. You don't generally plug it into a screen or a keyboard. You can remote in, and it is just its own little seismograph by itself, its own little device. So there are a couple ways. Let's switch over now to the screen, and we'll connect off of this. So you open a new tab, and you should be able, let's just check that we are connected to LANs. That's the network that the Ethernet is connected to. And this, typing in rs.local, should be able to take us, and it's a kind of port straight to the, if it identifies there's a Raspberry on the network, that it should take us straight to its IP address. So does that work? It doesn't look like it does.
Usually for Google Chrome, you have to do HTTP.
Oh, okay.
If you use Firefox, it should go rs.local straight.
Okay. Should we? Yeah, let's type that in. And if that doesn't work, there is one other way that you can. That looks like it's still not working. So let's try this.
I mistyped it.
Oh, okay. Let's try this other method called looking through an app to find all the IP addresses on your. Is that working right there? To find all the IP addresses on your LAN network. And we can do this if we switch over to the screen or the document cam again. I'll show my phone here. And what we're doing, I'm on an app called Fing, and Fing just searches and finds all of the IP addresses on the network. And here,
that's F-I-N-G, right?
F-I-N-G,
not
yeah.
Thing, but Fing.
Yes, Fing. And I'm looking for a Raspberry Shake, and I don't see one.
Let me make sure that I'm still on the same network that you are on. I'm still on LANs.
Let me make sure. Oh, maybe I'm on the wrong network.
Okay.
Here we go. Maybe. Still looking. I see one Raspberry Pi on the network. That is.
Does it have a SD card in the...
Right here.
Does it have an SD card in the thing?
Yep.
Yep.
Okay, we're checking that
So
we got it in there.
Let's try this that I found here on this generic Raspberry Pi. So let's try 10.
Okay.
10.60.0.154 and see if that works. No, it doesn't look like it.
Huh. Okay, well, we'll try one more time typing in that thing. We should be on the same LS.
If we need to, we can connect to this one.
Oh, we can?
Okay, so we can turn it back. So if we can't get that one to work.
What I'm noticing is our internet speed is getting a little bit low here. I wonder if all the everything is happening. It's kind of slowing us down a little bit.
No, I don't.
Sure that's this is connected.
That shouldn't slow us down.
I think it's finding it.
Then shouldn't it be showing?
Try one more time.
Like, this is a generic Raspberry
It's
Pi.
looking for something.
But it's not, I don't think it's
Resolving host, no internet.
I'm trying to reboot this.
Oh, really?
We sent over with your instructor's kit, and basically it takes the Wi-Fi and it'll allow you to plug in an Ethernet cord so that it goes out to your Raspberry Shake here. So here we go. We'll try this again. rs.local.
It's not plugged in yet.
Oh, it's not plugged in yet?
Or is it? It's plugged in.
Okay, that one's plugged in, and that power's on. Just so you can see what we got over there. Looks like it's all plugged in. Power's on. Everything should be
I still don't see it.
working. Okay, Well, you guys, this isn't the first time where we've intended to do something and then things just haven't worked out. So we'll give it another try here.
If we put that thing on AP2, we can connect to this Raspberry Shake.
Yeah.
Okay,
But-
why don't
Yeah. All right.
why
So
don't we try doing that?
we'll end this stream right now, and then we're going to start it right back up again so that we can jump over to AP2. Right? Because do I need to be on AP2 in order for this?
Oh, Chester, AP2 goes into
I'm on-
LAN. So
I'm on LANs right now.
So we're not going to just do the direct IP address of this. Might even
Wait,
change in the
don't change it yet.
Okay, I won't change
If
it.
you type in IP, probably will.
Yeah, it's 10
10 dot.
dot 71.0.138.
Yep.
Hey,
There
look,
you go.
it worked. Okay, so now we'll take a look here, and why don't we talk about what we're looking at here?
Here we're looking at basically your Raspberry Shake has its own web page. So this is the landing page when you type in the address it's on. It tells you the status. This is your Raspberry Pi model. The system status is running. What version of the software, the Raspberry Shake software you're on. Your IP address. The MAC address. Basically all computer stuff that your Raspberry Shake is on.
It's nowhere.
Whether or not you're producing data, you want this to be on. If it's off, that means your geophone's not working. Consumer on data forwarding, if you want to share your data with the entire world publicly or not, that's up to you, you're choosing. We encourage, of course, to share your data all over the world. I do anyway.
If you're not on that, if that thing is not on, you will not see your dot on that big map, right?
Right.
Okay,
Yeah, so if it's off, you're just collecting data on your local Raspberry Shake.
got
You're
it.
not sharing it. Server connection, because you're not sharing, you don't have a connection. And all the system info is down here.
Okay,
So,
cool. All right, so we've just set it up so that you get the basic thing happening. It's doing its thing. Now we do the next level of cool thing and say, I want this thing to be part of my classroom experience.
Switch the camera.
Oh, switch the camera. Okay, so here we go. There's that view, and here's that view right there. All right, Ben. This is Ben, everybody. Ben is one of our chief programmers here, and he's going to show us a little bit about what we want to do if we want to actually log into this Pi and start talking to it via Node-RED.
Okay, so do we have another Pi setup that we're going to send the data to? Or we can send it to this
send
one
it
up
to
here?
We'll send it to that one up there.
Okay, so that one's actually already set up in here. So if we come to the settings here into UDP streams, we have this one already set up. So they have the IP address of this LED matrix, which is actually printed on it, which is very useful.
Hold on a second, Ben. UDP, can you tell me what that means?
Yeah, so usually when you download a website, so UDP as opposed to TCP, they're both protocols. So a protocol is like a method of organizing the information you're using to communicate with someone. So for example, if you agree with a friend that if you send an urgent letter, you'd always use a red envelope, that would be a protocol because you would know from the envelope like the contents of the letter. It's going to be urgent.
Got it.
So TCP is what is usually used on the internet. It's like a strict protocol where everything is ordered and checked to see if the data is sending correctly or if it's corrupted. If the TCP packets come out of order to your computer will actually reorder them back into the order they were sent, and then only send the program that's waiting for it, like the data that it wants in the correct order, and everything's like certified and correct. But with UDP, it just sends like these raw data streams, which are just coming as like packets out of order, not even verified if they're correct.
Right.
It's much raw,
It's
simple,
raw data. Got
raw
it.
data. It's much simpler,
Okay.
which is lower latency, lower overhead. And with the kind of data we're getting from the sizeometer here, we don't want to be waiting for a missing packet. We don't mind if we just drop it or get it later.
Because you're getting so many packets every second coming out of that thing that it's just like,
yeah.
So what you're doing here is you're telling the Shake that you want it to go to this address up here for this Pi right there. So that's the target host that you type in. Got it. Okay. Cool. So that's there. Got that plugged in. And if I had a classroom with 10 different students working, I would put their 10 different IP addresses on there.
Yes, one of the other advantages of UDP versus TCP is that UDP can send it to multiple people at the same time. So
Okay.
this one data stream can be sent out to as many Raspberry Pis as we want. So like 100 or
So my
hundreds of
whole
Raspberry Pis.
group of students could all be working on this off of this one shake.
Yeah.
Awesome. Okay, cool. But I need to be on the same network, right?
Yes.
Okay. Okay, got it.
So that's the
s-
complication, but after that it's all easy.
Okay, awesome. So got that. Now what's next?
Okay, so next you want to actually do something with the data, which we already have set up on this Pi behind us. So you want to go to the Pi's IP address to access the node red. So let's go check what that was. 170 times 10.0.0.170. So I'm not used to this keyboard. I'm not used to this keyboard tool apparently. 10.71.0170 semicolon 18. It's loading.
It's loading. Okay, awesome. So I'll bring us back to our screen so we can see at least what we're looking at. There we go.
Okay, we have node red starting to load. Okay, this is
Wow.
that's the crazy air quality flow which we don't need to look at.
Got it.
Here is the kind of complicated. So this is after we set up everything. So this is the final version of the flow.
Okay.
We can make another flow and start from scratch if you want.
Yeah, that might be good just so that we know
Okay,
what
we'll
we got.
steal this node here. 'Cause
Yes.
we're gonna set that up. Anyway.
Love stealing nodes.
Okay, so we disable this flow. So then we'll see the screen behind us. We'll stop displaying that stuff. Yeah.
Okay, yeah.
Cool. So here we have a UDP in node. So all this node does is it takes any UDP messages which arrive on this port, which is the same port we've told the Raspberry Shake to send data to, and it can add outputs that the raw message that it receives. So it's telling its output as a string. And if we pull in a debug node here, then we can actually see what data the Shake is sending to this Pi and how the Pi is receiving it. So if we deploy, we can look over here at the debug,
Oh,
and this is
wow.
how much data we're receiving. It's like hundreds of packets a minute, and each one of these packets contains multiple data points. So if
Wow.
we pause this here, so we can actually get one of these packets and look at it. If when I like, I thought there was a way to open the full string. Maybe that is the full string. Anyway, so here we have one packet. It says the data channel, which is EHZ.
Mhm.
This number here is a timestamp. This is like Unix time. This is the amount of seconds since like 1973 or something.
Got it.
It's like 15 million seconds, something like that. And then each one of these values is a what is it? Micrometers per second acceleration. Each
Yeah.
one of these values is the raw data we're going to be working with. So that's how many samples you get per packet, and you get hundreds of packets a minute.
Cool.
So too much data to display on this screen, which only updates a certain number of times per second. But we can get nicer than this. The Raspberry Shake folks have made a nice parser node here.
Right. And on the tutorial down below that I'll link to in this video, I'll show you guys how to go and grab the Raspberry Shake parser from the palette up there. You have to actually install this because it doesn't come default on your Shake or on your Pi.
Yeah.
Most of your Pis. Some of the newer ones might have it
Yeah.
built in.
So now we can see what kind of data that the parser is giving us.
Parsing is like it cuts it up, right? It does something like that.
It's like interpreting the data.
Oh, okay.
So this is the same packet as before, except now it's being interpreted by this other node here. So instead of before when we just saw the timestamp and this thing as a string where we had to like look at it and say, oh, what is this part? What is this part? Now it tells us the channel directly is EHZ, the timestamp is this, and it also tells us the timestamp range. So
Cool.
I think each one of these samples is like 1 millisecond, and then it's telling us that since the last timestamp it's been 50 milliseconds, something like that. There is a way to interpret this. I just don't remember the exact details.
That's right. Cool. So the Raspberry Shake parses the data that goes along with the geophone there. Perfect. Now, how do you make it do something cool like display up there on on a sign, or just make it display anything. Like will this graph itself if we put a graph in here or do something like that?
So if we tried to graph this, we couldn't because it's an object which has all this data inside it.
Oh, right.
What we want is to get some numbers out of this.
Got it.
Some
average numbers or something.
Yeah. So if we come back to our other flow here, you can get these function nodes off of the tutorial.
Okay, I see.
So this is a function node we made, which is the average magnitude. So the numbers are positive and negative numbers. When the seismograph or the sensor,
geophone,
the geophone, that's what I thought it was, goes up and down. If it goes down, it can sense that acceleration and it can give us a negative number. And if it's accelerated upwards, it can sense that acceleration and give us a positive number. But if we were to average that over a period of a second, say it went up and down the same amount, we get a really low or even a zero value, even though the thing was shaking a whole bunch. So what we do is we take the absolute value, which means all the negative numbers get turned into positive numbers.
I see.
So it's not anymore the exact kind of seismometer graph you're used to seeing where it goes up and down like that. It's now more of just a total vibration over that time period instead of what the ground was doing. It tells you the ground was doing something.
Cool. So
we can steal this function node out of this flow and into our flow here.
And do you think the Raspberry Shake guys wrote that, or did you write that?
I wrote this function.
Oh, cool. Thank you.
So then we can let me turn this one back on. So this is what the numbers look like now that we're averaging.
Ah, those are things you can graph.
Yeah, so if you bump the table, that's actually the wrong table. If we bump this table, you should be able to see those numbers go up.
Oh yeah, totally.
Shaking. So I've tested it where if you're walking on this side of the room, you can see your footsteps.
Really?
If you jump, you can definitely see it.
Wow.
So it is pretty sensitive, and that's not even that rigorously set up. It's just in a box over there.
Huh.
I'm sure if you put it on the actual concrete floor, screwed down, it'd be
even better.
It'd be better, yeah.
Wow. So just think of the applications. Anything that causes vibrations could trigger this thing. And then if we put a switch node or something like that in there, it could say if then do this.
Yeah, so we can get a fancy graph out of this. And how we do that is with this switch node. Let's check this what this is doing. Okay, we can just steal these nodes. They are slightly complicated, but we do provide them on the website. Basically, it switches. This switch node checks what channel the data is, and then each one of these channels will come out one of these outputs. So we only have one sensor on our Raspberry Shake, which is the Z-axis, but the 4D has sensors for 4 axes.
Yeah, that's the pressure one and everything.
Okay.
Yeah.
So the 3D can do all 3 axes as sensors pointing in different directions. This one only shows the vibration up and down.
Okay.
So put this switch node on here. This one does all kinds of crazy formatting the graph ones.
Wow.
Which we provide that, so you don't have to worry about that. That would be annoying to do yourself. So we can deploy this one. Okay, so you kind of see the graph here. What you do to find the graph is you come to the same URL that you used to go to Node-RED. So we'll copy that. And then add /vy at the end.
Is
it command?
It's Command V. Yeah. Command C, Command V. Ben's not used to working on a Mac.
Okay, that's loading right now.
It's okay. There we go. Ooh, I'm excited. Now, why is it taking more than a second? Because it's probably processing it.
Okay, the reason this one is slow is because it's doing a bunch of work to make the screen work.
Oh, I see.
It takes a lot of resources.
Right, because we told it could work the screen right now, or the screen is still working in the background.
Right when I tapped out. Okay, there it is.
There it is. Wow.
So you can see how fast it's updating. It's many times a second.
Okay, and look, I'm vibrating, and look at
that was just noise before. Now you can see the real data.
Wow. If I just give it a little tap on the table, then it comes on. Cool. Okay, so if I made if it reaches this level, then set off an alarm, or then do a buzzer, or then do anything, that's all within the scopability of Node-RED right now. It's once I know this 200,000 is the number of vibrations per second, or the magnitude of the vibrations or something. Yeah, we'll have to ask Jefferson on what exactly those things are, unless you know.
It's like micrometers a second acceleration.
Okay.
I don't know exactly.
So can you show us, how did you make it? So this guy still isn't turned on. It's in the back of our room, but can we send the data over there?
Yeah, so with our LED matrix library, it's actually pretty simple. So we'll delete this. We don't want that anymore. Let's redeploy. So when you have the LED matrix on your site, then it comes with all the LED matrix nodes, which are down here somewhere. Here we go, text to matrix. So all we'd have to do to get the average magnitude on the screen is just stick it in a text to matrix node. Make sure these settings are all the same. So we can put a prefix text of micrometer per second acceleration, and then deploy that.
And then right up there behind us.
There it is.
Yay! All right, it worked.
And then if you want to have buzzers go off and stuff, you'd have a I don't know if this example has it. No,
RPI.
You'd have a switch node, and then you'd put send like 1 or 0 to a certain pin, but we don't have that kind of output on the all the pins are taken up. That's how that would work. Okay,
cool. Well, thank you, Ben, and thank you, everybody. I hope that this was pretty informative for you guys today. Obviously, this Raspberry Shake has a lot of potential. We do hope that you and your students mess around with this and come up with some cool examples. And then please don't forget to share what you come up with on the forum. And as always, you know, post, chat, and if you want to subscribe to our channel, you're welcome to. And then when we get more cool updates, we'll add to it. But we're unlocking a really powerful seismology level detector that can detect earthquakes around the world, and can also be used in our classroom and in all sorts of places. Our hope is, in the end here, when your students start to see what can be done with this, then you can ask the questions, how could I correlate this shaking to things that I notice outside in our environment? Maybe there's a new roadway going in, or maybe there's Jefferson told me about some students that he worked with where they wanted to set up a shake on a railroad track to identify when new trains are coming. And if the railroad track started shaking, then it would make a sign go off or something like that to say, watch out, time to be careful. But as for always, thank you very much for joining us today. And yeah, we'll see you next time. T3 out.